Welcome. In this lecture, which has multiple sessions, we'll explore nonlinear least squares. We'll end by looking at the Levenberg-Marquardt algorithm for solving it. So the main concepts in this lecture are: what are nonlinear least squares problems? How can we perform a linear approximation to the nonlinear problem? The Gauss-Newton method will turn out to be an altered form of steepest descent. The Levenberg-Marquardt algorithm is also altered descent. And one sample problem that we can look at is how to solve the GPS localization problem. So GPS is the global positioning system. Let's take a 2D simplified example. Let's suppose that we're in 2 dimensions, and so here we are on the surface of the Earth, and there are 3 satellites in orbit, and we'll suppose that they're in a common circular orbit, which is a reasonable approximation to what we have on Earth. So what a user receiver knows is they know the time that they received it, and then each one of these GPS satellites is sending a package of information, and that package of information includes their estimated 3D local position, and it also includes the time that the transmission was sent. If the receiver subtracts the true time of receipt minus the time of sending, then that gives a pseudo time in between, and that'll be approximate because there are some clock errors. From that time, they can estimate a pseudo range based on the speed of light, which is presumed to be constant. From the receiver point of view, each one of these satellites is somewhere on an arc of radius of a pseudo range, and the problem is that the receiver doesn't know their exact location. One way that we can formulate this using a nonlinear least squares problem is we could draw circles of that pseudo range around each satellite. So here we have satellite 1 with its pseudo range circle. Here we have satellite 2 with its pseudo range circle, and satellite 3 with its pseudo range circle. And the receiver, in an ideal situation, is at the intersection of the constraint circles, and for an approximation, the receiver is somewhere near where these circles don't exactly come together. So this is an example of an optimization problem, and in the next sessions we'll formulate this as a nonlinear least squares problem.